Hello, we are going to learn about the quantum mechanics, and the first lecture was that wave function and its related topic. Now we'll use some quantum mechanical operator on the wave function. And what is the quantum mechanical operator? And with the quantum mechanical operator, we can change a function to the another function. So quantum mechanical operator, in this position, at first we learn about quantum mechanical operator, then its position operator, momentum operator, energy operator, and they are actually linear operator. I will discuss it. Then commutator, eigenfunction and eigenvalues, expectation or average values of dynamic variable. And dynamic variable, what is dynamic variable? It is maybe a position. With time it can change of any particle. Momentum may be changed, so it is also a dynamic variable. Energy, kinetic energy or another energy, with the position it may change, no problem. So energy, position, momentum, they are dynamic variable. Now what is operator? Operator in quantum mechanics is a mathematical tools or mathematical rule or tools. What is this? A mathematical tools. What is mathematical tools? Here mathematical tools may be a derivative, may be an integration, no problem. So operator is a mathematical rule or tools बोलते पारी, tools which can operate on a dynamic variable to give another function, or which can operate on a function to gives another function. Okay, now how we can explain different operator? We may use just a position, dynamic variable position. So x is a position, it is a dynamic variable. P is a momentum, it is dynamic variable. E is a energy, may be dynamic variable, and they are also can use as a operator. And at first, to go to operator, we learn the commutator. What is commutator? Commutator, because we will use commutative rule in dynamic variable and the operator. So we already learned about the operator. Operator is a mathematical tools and it is denoted by or operator denoted by just a cap, or if it is position operator then x cap, if it is momentum operator then p cap, if it is energy operator then E cap, in this way. Let us consider two operator alpha and beta. Now we define commutator. If alpha and beta, if alpha operator and beta operator are two operators, the commutator bracket operator are two operators. The commutator bracket what is this type of bracket? This third bracket of this two operator represented as what? Third bracket alpha operator comma beta operator, third bracket closed, and it defined as alpha beta, that is alpha operator comma beta operator equal to alpha operator beta operator minus beta operator alpha operator. Now if alpha operator beta operator minus beta operator alpha operator is equal to 0, if this equal to 0, then this two operator is commutative, then these two alpha beta is commutative, and if alpha operator beta operator minus beta operator alpha operator not equal to 0, then it is a non-commutative operator, then these are non-commutative. Okay, so now we can use some real example without alpha beta. What happened? Let us consider del x operator and del 2 del x2, this is comma, that is actually alpha and this is actually beta, then is it commutator or non-commutator? Now to find its commutative rule, or if it is commutator or non-commutator, then we should take a function on which this operator can operate. Let us consider a function fx. What is this? Fx is a function, that's mean it depends on x, that's mean it may be position, Then what happened? What happened? Del x comma del 2 del x2 third bracket in fx, that is this operator function on it. Then what happened? This is commutative or non-commutative? We don't know. Then what happened? Del x into del 2 del x2 minus del 2 del x2 into del x. It is fx. Okay. Then what happened? If fx you can multiply, then del x del 2 del x2 fx minus del 2 del x2 into del x fx. If del x is a mathematical tool, that is derivative, just a simple derivative, then what happened? First derivative was f dash, then second derivative f double dash, and third derivative it may be f triple dash. Okay, and here it is also first derivative, it is second derivative, so it is minus also f triple dash x, just derivative. So this will be cancelled out, then it equal to 0. Hence we can say del x del 2 del x2, these two operator is commutator. This two operator is commutator operator. Okay. And now we can take another example. We can use another example. Let us consider, let x del x, is this commutator? Then again we can verify it by taking a function. Let us a function fx, so x into del x minus del x into x fx equal to, this is the commutative rule, equal to, what is this? It is 1. It is 1 actually. Then what happened? X del x f x minus, this is actually 1, then just fx. And what is this? X into f dash x minus fx. So what happened here? Here this is not cancelled out. So del x del x fx, sorry fx x equal to this, and x del x not equal to 0. Hence we can say x del x is not a commutative operator, or they are not commute to each other. And we can take another example, no problem. Let us consider del x and del t Is it commutator? We don't know. Then we should verify it. Then take a function f. Take a function f. Then what happen? Del x into del t minus del t del x f or x maybe. Then what happen here? Del 2 del x del t minus del 2 del t del x f, and since it is a just position and it is time, so this is the multiplication just, and this may cancel out this. So what is this? And since it is del 2 del x del t f minus del 2 del t del x f, so this is cancel out, equal to 0. So they can commute to each other. So del x del t is a commutator. They are commutator. No problem. Now momentum operator. The position operator is just x. Okay, position operator is just x, and we can use just x. This operator equal to x. No problem. But what is the momentum operator? Momentum operator. We know the wave function and what is the acceptable wave function also we can discuss the last lecture. Let the wave function for a free particle in a positive x direction psi already discussed about this x t equal to a into e to the power I k x minus wt. This is a wave function. This type of wave function is very acceptable wave function, and this is a general type of wave function we can use in physics, chemistry, biology, not biology, in any quantum mechanical operation. Now, if we use just a linear operator, just a derivative, then del x del xt equal to del x a into e to the power I k x minus omega t. Then what happened here? What happened here? This is actually a, then e to the power I k x minus omega t into I k. Since it is a position operator actually, sorry, not a position operator, it is derivative with respect to position. Then this term, the derivative of omega t must be 0. Hence I k a e to the power I kx minus omega t. Okay, and what is this? This is the original wave function. So del x is a operator which can operate and gives another function. Okay, now what happened? If we rearrange it, that is, if we multiply in the left hand side by a cut by I, then del x psi xt equal to I a cut by I into this term comes from the outside. We can multiply this in the both side. Then what happened? I into k, and this is actually psi xt, Now from the both side, if we remove psi xt, then what happened? A cut by I del x equal to a cut by I into I k. Now I is cancel out, I is cancel out. Okay, then what happened? Then a cut by I equal to a cut k. Now what was the k? It is constant. Okay, no problem. But what is the value of k? From de Broglie equation, momentum p equal to h by lambda. Okay, now p equal to, if we multiply by 2 pi, then we can divide by 2 pi. H by 2 pi, then what happened? 2 pi by lambda, no problem, 2 pi by lambda. Now p equal to, what is this? This is actually h cut. This is actually h cut, and this is the k. This is the k. Clear? So del x, what is this? Clear? Then what happened? H cut by I del x equal to h cut into 2 pi by lambda. Okay, 2 pi by lambda, that is actually k. So what happened? This is actually p. Okay, then k, this h cut into k. So this is h cut into k. This is actually momentum. So we can rewrite this. This is a momentum, and since it is only in x direction, then this momentum is only x direction. Hence we can say the momentum operator, if it is cap, then this is the momentum operator, is cut by I del x, that is in x direction. The momentum operator is h cut by I del x, or we can say minus I a squared del x. We can multiply by I in denominator and we can get minus I, no problem. So this is the momentum operator in x direction. Then what happened in y direction? P cap in y equal to minus I a squared del y, or pz cap equal to minus I a squared del z. Hence this is actually the momentum operator, and this momentum operator we can use to get the momentum or the expectation value of some momentum, okay, and to calculate some real value of momentum of some dynamical particle, okay.